Good afternoon, everyone. I'm Abhay from EDS Technologies. First of all, we thank you for taking your time out and joining our webinar today on enhancing structural performance and efficiency of composites with SIMULIA Abaqus. I would like to begin this webinar by giving a short introduction about our company, EDS Technologies. EDS Technologies was incorporated in 1994 to focus on providing PLM solutions, implementation, and support. We are the largest technology solutions provider in India and platinum partner to Dassault Systems. We have served more than 2,000 customers and operate in 10 locations across India, with our headquarters being at Bangalore. We also have strategic partnerships with world leaders like EOS for additive manufacturing requirements, Human Solutions for ergonomic solutions for automotive and aerospace industries, Technia for ensuring product data quality, for military simulation and training needs of aerospace and the defense industry, we have partnered with Mac Technologies for visual simulation solutions. We also have strategic partnership with Esri for GIS requirements, and with respect to EDA and optical design solutions, we closely work with Synopsys. We have a dedicated sales, support, marketing, and customer satisfaction teams to address customers' business and support requirements. The speaker for today's webinar will be Dr. Danish Handa. Dr. Danish has completed his PhD from IIST, specialized in the field of composites, and has several Scopus indexed publications. He currently works as a solution consultant for SIMULIA at EDS Technologies, and he has been using SIMULIA for more than 12 years and has more than 3 years of industry experience. He works with many composite manufacturers and research institutions to improve their existing design practices and methodologies. Over to you, Danish.
Thank you, Abhay. Good afternoon to all. So I'll be giving the short session on composite simulation using SIMULIA as a platform. Starting with introduction, then what is SIMULIA and what does it do? Basic of composite simulation, case studies on composites, and I have also filtered in a way that we will be conducting a separate seminar on what can be further enhancement in the field of composites using SIMULIA product, and then the customer references. So moving towards SIMULIA as a portfolio, so it's not only Abaqus, as many of us know that Abaqus is a FEA tool, but in a portfolio we do have 4 different softwares. First one is Abaqus, which we are well known with, that is from geometry to modeling, meshing, loads, boundary conditions, and solving. We can do pre and post processing. So this will be having entire portfolio including explicit, implicit analysis, dynamic analysis, etc. Moving toward FESafe. FESafe is for fatigue and durability analysis. We'll be getting log life, damage life, etc. Third one is EyeSight. EyeSight is completely for a parametric optimization, where you will be having your design space, performance, cost efficiencies, etc. Fourth one is Tosca, that is for non-parametric optimization, where you can optimize your product in a way where you are not playing with any of the parameters and you want to still have a good strength with respect to your products. So these 4 softwares make a SIMULIA as a portfolio. So moving towards our topic, that is overview of composite simulation. So we'll be having an entire overview of how we can model and simulate the composite products or composite components in SIMULIA with various applications. Starting with basic of composite simulation. So as we all know, we are composite expert here. We have composites with different layup orientations. So in our software, that is Abaqus, we can do it in very easy way. So for example, there is a plate which you can see. I have partitioned the plate into 3 different partitions and have given layups. You can see in the left hand side where my cursor is there, ply name. Different ply names are given. Regions have been selected. Materials, we have used glass epoxy as well as aluminium. Thickness, we can give variable thicknesses or whatever we want. We can select the rotation angle. We can select the even your Cartesian coordinates, whatever you would like to add, or its global coordinates or local coordinates, whatever you want. So we also do have a visualization portfolio here. So what we can do is, suppose we are having a particular plate with a partition, you can visualize that these particular plate or area has been given such layups. You can see here the layups are in 45, 60, and even you can have a ply count of ply 1 to 5 with different thicknesses. And if you want to have different ply orientation angles, that can also be possible with a single click. Whereas in the middle of the plate, middle area of the plate, we have 10 different plies. You can see with visualization, with thicknesses, ply names, and even the orientation effects. So this is one of the key areas that it's very nice for our customers or the manufacturers to understand what kind of layup we are manufacturing, as well as what kind of layup we are doing for a simulation base. Then loading and boundary conditions we can provide with respect to thermal loadings, dynamic loadings, even vibration, noise, structural loading, we can definitely apply here. And then we can get the whatever results we want, whether it's a criteria known as psi hill, psi wu, or something. Here, another beauty is we can also visualize the things in ply by ply effect. Suppose, for example, ply 1 is available in all the 3 areas, so we can get the results of the stresses for ply 1. However, at the middle area, I told there are extra plies, 5 extra plies. So ply 5 copy 1 is the name. It is not there in any of the 2 areas, but at the middle. So you can come to know a single ply is having how much stresses, and even for the whole component. Then now I'll be moving towards some global case studies for composites which we have performed successfully for our customers. I'll be showcasing you on different applications, including drones, honeycomb structure, airplanes, yachts, etc. So I'll start with the basic thing, that is your tensile testing, because this is the basic what every researcher or a manufacturing does when they prepare their own prepregs or components and they need to test their component. So first thing which we need to do is a tensile test. So for tensile test, we do have in the property module, we can choose our own composite, whether it's a glass, aramid, or carbon, whatever we need to use. And we need to provide 3-dimensional properties. Even we have to provide damages such as Hashim damage, for example, here I have used. And then we can create our own sectioning. Here I have used solid as a property section. We can use both solid and shell elements. And in a single module, you can create your own sectioning and give the material orientation. So assign material orientation, and you can assign the entire component as a material orientation. Sorry. Yeah. So moving towards next thing, now we have to produce a crack. So in a realistic simulation, we expect that the crack will be at a position which is center. So we have to generate a crack using XFEM technique. So XFEM is nothing but an extended finite element technique, what we use to analyze the crack propagation in a material. So here, based on Griffith's theory, this particular thing is added. And then when we visualize the results, you can see the realistic view of the results. This is how the tensile test will be happening. So it will save a lot of money, lot of time of the manufacturers which are conducting mechanical testing. It is expensive as well, so it will save a lot of money and time. We do get stress strain curves or stress or distance curves with respect to composite, and it's a very realistic curve what we have got. Second thing is virtual crack closure technique. This is used where your debonding or delamination effects come into picture. So for example, we have selected 2 beams. These beams represent carbon fiber and a bond, that is, we have considered epoxy as a bond here. And we have to give an interaction over here that we have given as a cohesive elements that is used as an interaction property here. And we have given a surface to surface contact and a cohesive element contact, where we are using our fracture criterion, our tangential and normal behaviors. And then again, as I told, we need to have a crack using a virtual crack closure technique. There are three methods. One is contoured integral, XFM, and virtual crack closure. So XFM we have seen in the previous slides. This is a virtual crack closure technique. So this is how the entire thing will be built up, and we can move ahead. So this is how it will be shown. So the bonding effect or the delamination effect can be easily modeled using SIMULIA. Moving towards another case study, this is for impact load, specifically for bulletproof jacketing or a bird strike. So we have considered different sectioning, different plies. This is also a solid ply. Here we have used carbon fiber as a material with respect to epoxy, and we have used several different plies and chosen a solid as our property. The loading conditions, it's fixed in the entire area, and at the center the ball has been given a velocity, so it will be having an impact load on this particular plies. So this is how it looks like, and if you can see the zoomed version of it, so you can see various plies getting fractured, and we can even visualize the single ply effect of single ply, how it is behaving. So normally in composites we do play with the orientation rather than playing with the thicknesses, unlike metals. Metals we can increase the thickness, but for composites always better to play with thicknesses because of the higher strength in various direction depending on the application. So here we can analyze a single ply with respect to all the plies. So this was a wing simulation. The wing was designed by Boeing. So we have taken the reference from there and we have done the simulation. This is the combination of aluminium as well as carbon fiber, and having the effect of a fixed at one end and the loading condition at the other end. And you can see here we have different ply orientations, loading conditions. And you can see the ply count here. 4 is the ply count for our composites, and single is the ply count for aluminium based. So this was a very simplified simulation showing the cantilever effect. This is very interesting. This is for yacht hull. We have around 108 ply counts in one area and 78 ply counts. This is a patchwise effect. Why patchwise effect? Because sometimes we need to play with the thicknesses as well with respect to orientations. So what we have done is effect of reinforcement. What happens with composites, as we all know, that somewhere the stresses are very high, somewhere it's low. So we keep the other area as thicker comparative to the area where the stresses are low. So there where reinforcement plays a major role. So what we have done here is we have inputted a patchwise direction of core, glass epoxy, aluminium, all these things are integrated together and we have put it here. And loading condition, we have provided all the loads such as hydrostatic, inertial relief, mass loads, all the things which are realistic in the ocean scenario. So moving towards the results. So this was the results, and here also, as I mentioned previously, we can perform the analysis using single ply. So here we can select any of the plies. For example, in this case, if I select the top hull and I'm selecting a third ply, so only the results of third ply will be visualized, and we can come to know, okay, this is the position where your stresses are very high, so we need to have an extra patch over here to avoid such kind of high stress regions. So instead of applying the another sheet of carbon or glass fiber on the entire hull, a patch can be applied on or a reinforcement can be applied on a particular area to avoid such high stresses. So this is one betterment in the simulation industry which we can follow rather than applying directly on the component, which can be very expensive in nature. So another one thing is honeycomb structure. We do model honeycomb structure in CAD models, but we need not to do. We have a honeycomb structure plugin here where we can directly make a honeycomb structure out of length, width, height, cell size, everything, and a honeycomb structure is ready for you. We can apply face sheet as carbon fibers, honeycomb structure as an aluminium structure with all the failure properties. For aluminium, we can use Johnson-Cook model. For CFRP, we can use Hashin damage criteria to model these particular composites. Then we have the layups, as I already told you earlier, how we can give the layer. We can pick the sectioning. We can create our own coordinate systems if we want layup in different directions. Then we have assembled it. So this is how a proper honeycomb structure can be made. That is a sandwich structure. We have given 3 different loading conditions to understand how these things do work. So first loading condition is when it's a tensile load and the bonding strength is very high. So there is a probability that the aluminum can deform. Second is when it is a compressive test basically. Here also, if you can see, the strengths are very high. So there is a high chance the aluminum can deform, but it is not in a complete failure stage. So third result is again when the face sheet bonding strength is very low. So there is no deformation in the aluminum, and the face sheet can be lifted out easily using a peel ply test and everything. Another case study is about the windmill simulation. So we can have n number of CAD files that can be from SolidWorks, CATIA, UG, anything. We do have integrated things to read all these files. Here also we have used composites as our wing layups and aluminium as our entire structure of the windmill. So after doing the things, we are assembling the particular entire windmill to understand the stresses due to the velocities that we are providing. This is due to the air velocities, how many stresses can be generated in the entire windmill in the wings region. So this is the kind of studies we have performed for a customer. Another bigger area is the drone simulation. Nowadays, many drone startups has been launched and they are doing pretty well. And few of the drone startups have used our simulation tool to get the DGCA certifications based on the simulation effect. Here, this is a small example of wings are of carbon fiber and how if the impact load or any kind of load is acting, how the wings can fail. Normally, it is suggested that the failure of the such things are brittle in nature, so we need to verify it. So this is the assembly of the entire drone, and we have given the loads on the wings itself and kept everything as a rigid part. And this is how the wings are getting break due to the excessive loads. And this is another good study of airplane crash. So what we have done is we have created a concrete wall, and then airplane is made up, one airplane is made up of aluminium and another one completely of CFRPs, and we are comparing the results based on the deformations and stresses that has been generated. So we can clear cut see in the next video like how the difference is there in the fracture. So if you see about the carbon fiber first results, you can see there is a crash test that is happening with respect to the concrete wall, which is very rigid in nature. That is why the deformation is not happening in the concrete, because it is been noted that it is rigid in nature. So if we see the crash of carbon fibers, you can directly see it's crashing in a very carbon fiber way, how it should be. And the deformation is hardly there in the later part of the aircraft. Whereas if you see about the aluminium structure, you can see the deformations will be very high and it is going to the entire aircraft. So that is why nowadays many of the aircrafts, almost 70 to 75% has the skin of the aircrafts or the parts of the aircrafts are be made with respect to different fibers such as glass, Kevlar, or carbon. So this was about the entire webinar. I just wanted to tell you about how basically we can transform the things in a better way using simulation tools, and to save the money, and to how we can give the ply orientation in a better way to have a better sustainability. We do have some important topics which we need to cover in the upcoming webinar. One is with respect to random fibers. So nowadays, a lot of studies has been doing, or people are doing a lot of research on how we can implement the randomness in the fiber orientations, or suppose we are doing kind of injection molding or kind of chopped fiber carbon nanotubes into a particular component, or while repairing we are using a chopped fiber mat or something, how this can be studied in a stage. So we as team medias are creating some codings in using Python and Fortran to understand the behavior of random fibers which should not overlap upon each other, how this randomness can be created with respect to the fiber volume fraction, what kind of resin can be used, what kind of fibers can be used. So everything has been taken care, and we can have a study based on micro scale as well as macro scale. So we can scale down the problem as well as scale up the problem. So we are working on that. We are creating our own codes to study in a better way. So this is one of the studies which will be it will be upcoming in the next webinar. Then we do have right now, whatever studies I have shown you is with respect to unidirectional fibers, but we do have the capability of modeling and simulation of bidirectional fibers as well, both in a unit cell way as well as in the component level way. And the beauty of the software is we do have a RV plugin, representative volume element method. So it uses the Mori-Tanaka equations to, if suppose your vendor or your provider of the material has given only two-dimensional properties, and you are not having the three-dimensional properties to add into the software in the material properties. So what we can do is we can input the two-dimensional properties, input the density as well as fiber volume fraction. Based on Mori-Tanaka equations, it will automatically calculate the ABD matrix and give you the three-dimensional properties of a fiber based on the volume fraction as well as densities. So this can be automatically done, and once you get the properties, you can do it in a component level way. So this is a plugin that Deso is providing with SIMULIA. Second thing is we do have different weaving patterns. So for example, the weave is not always same. It may be satin weave or plain weave or twill weave. So weaving effects can also be shown in a way in the particular software. Moreover, we can also perform unit cell methods. That is your characteristics of fiber and matrix in a different way, and you can merge in a component level way. So these are all things we can perform in SIMULIA as a portfolio. In addition to that, we do have, as I already told, uh, optimization techniques. We have parametric optimization known as eyesight. So if we are designing some component and we want to have a parametric optimization of that, we want to reduce the length, thickness or height, anything, whatever we want, and without losing its strength, that can also be performed in a single click. We can get many iterations. First simulation you need to perform in Abaqus, and then the ODB file or the output file of the Abaqus is known as ODB file. That can be directly transformed into eyesight, and they can perform the simulation for you, and then you can get the optimized result. Then another interesting thing is that is C-zone simulation. It is nothing but the crushing simulation. It is a paid plugin provided by Deso using SIMULIA. So for example, a F1 car is there and it has bumped into a rigid pole. So how this pole can cause the effect on the wings that are made up of fibers, and these all studies can be easily performed using our software. And what all optimizations are required, or what all fiber orientations or fiber effects are required to solve these particular things can be easily studied. How much thickness is required to avoid such kind of high catastrophic failures, all things can be easily studied in that. So this all things I will be showcasing in the upcoming webinars, how we can play around with bidirectional fibers, how we can do the analysis using RV methods, how we can use bidirectional composites. And there is another thing which is known as composite modeler as a plugin. So what we can do in that plugin is, like, we have a Deso portfolio, we have CATIA composites as a modeler. So we can model entire layer. For example, if we tell about the wing structure, it is not straight in nature, it has a tapered section. So it's always very difficult to model tapered composites because the fiber orientation, how to place in simulation is difficult. So in CATIA composites, what we can do is we can have entire layup in a nick of time, and that layup file can be directly imported into Abaqus and can be directly integrated over the component. So by that, you can easily perform your simulation using a tapered section. So this also we have performed for one of an esteemed customer, and they have successfully done it, and we are in continuous interaction with them. So this was all about the brief about the what capabilities SIMULIA is having in terms of composites. We do have other solutions with respect to not only for composites but integrated with respect to metals, rubbers, polymers. So even we have analysis like vibration. We do have analysis like all the dynamic effects with respect to winds. We can create the scenarios of fluid. So it's a complete solution where you can perform dynamic, non-dynamic, explicit, implicit, non-linear, linear, as well as a particular kind of fluid problems as a scenario, but not a CFD software. So this, and we do have good customer references where we have successfully given the support and gained a lot of acknowledgements in terms of composites. Thank you so much.
So, yeah, I would like to thank Dr. Danish for delivering a very informative webinar. I'm
Thank you.
confident that it was helpful for our audience as well. I would like to thank the audience as well for taking their time out and joining us for this session. If you have any further queries or questions related to our subject matter or any other simulation requirements, you can always connect with us. Our details are displayed on the screen right now. You can reach out to us anytime and we'll be happy to address your queries. Please do keep an eye out for our upcoming seminars and webinars and other planned series in the composites topic. Please do follow us on our social media for the same. Thank you once again for joining us today. See you at the next session.